All right, so today's lesson is going to be an introduction to graphing exponential functions. So exponential functions are really relevant in the real world. Albert Einstein once said that compound interest is the most powerful force in the world, and that's coming from someone that split an atom. So real power behind what we're about to learn this unit. All right, so let's take a look at what exponential growth is. So if you, what happens if you invest $100 in the stock market and it earns 10% every year? So if we just look at our basic math here, if we take $100 and we multiply it by 10%, how much interest did you earn? All right, so 10% as a decimal is just 0.1. So 100 times 0.1 is 10. You earn $10. All right, and so do you earn $10 every year? All right, well, if it's simple interest, then the answer is yes. You only earn interest on that principal amount and not on your interest. But in the real world, that money is yours. It goes into it. So now we have 110 bucks. In the following year, you're going to earn 10% on that, which is 11. So the second you earned more money. Okay, now you have $121. Okay, and you'll earn 10% on that, and so on and so on and so on. It's going to keep growing. Right? You're going to earn more money every year. Eventually, it starts to get really big over a period of time. All right, so what is this? Okay, this is a geometric sequence. All right, these numbers right here, 100, 110, 121, this is a geometric sequence. So what we're really doing is to figure out what we get next in the sequence. So you start with 100. What comes next in the sequence? What do I have to multiply 100 by to get 110? We're going to multiply that by 1.1. Not just 0.1. 0.1 gives us the 10, but then you have to add it back to 100% of the original thing. Okay, and this is going to get us 110. All right, so if I want to know after 2 years, right, what am I going to do? I'm going to take the 100 and multiply by 1.1. That gets me 1 year. Then I'm going to multiply by 1.1 again. All right, and so that's going to get me 100 times 1.1 squared. All right, and then if I want to do it 3 years, how much money am I going to have after 3 years? It would be 100 times 1.1 times 1.1 times 1.1, which is 1.1 cubed. Right, and so we're seeing this pattern. So if I don't know how many years I want to create a general formula, right? It's going to be 100. So for n years, it's going to be 100 times 1.1 n times. So we just say to the nth power. Right? And so what we created here is the explicit formula for a geometric sequence. Right? We have our common ratio, what we multiply every time to get the next number, that's 1.1. And so how many times do we want to do it? That's going to be our n, so the number of terms in the sequence. In this case, the terms are years. All right, and so eventually, if n is big enough, this is going to be a pretty large number. That 100 is going to grow by a lot. All right, so that's what interest is doing. All right, it's compounding. The money that you earn starts to earn money. All right, so let's do a quick review of geometric sequences. All right, so here's that same sequence we were just looking at. Okay, after 0 years, we have $100. After 1 year, 110, 2 years, 121, and so on. All right, and so we know, because we just did it, that the interest rate was 10% and the growth factor, the common ratio, was 1.1. But let's look at this and say, how do we figure this out? All right, so we are going to turn this into an explicit ratio or an explicit formula, and to do that, we need to know the common ratio. So let's look, we have 2 different explicit formulas up here. Okay, the first one is very common for a sequence, because sequences usually start at the first term, or actually they do start at the first term. So it's the first term, f of 1, times your common ratio raised to the n minus 1 power. All right, and so that's how we just need to know the r. We know the first term already. The first term is 110, right? We don't know r yet. Or we could do this form. This is very similar. Right? It's f of 0, so the 0 term times the common ratio raised to the n. All right, so if you start the 0 term, we don't have to worry about the n minus. We don't have to shift it one spot to the right. But here we know the 0 term is 100. Okay, how do we find r? So we already know from the previous problem r is 1.1. Okay, but how do we figure that out? So if you have this sequence here, to figure out r, you just have to divide, right, the second one by the first one, the third one by the second one, and so on. And if it's the same, then you have a common ratio. So 110 divided by 100 equals 1.1. 121 divided by 100 and 10 equals 1.1. 133.1 divided by 121 equals 1.1. So every time it's 1.1, which means I'm multiplying by 1.1 every time to get the next number. So in this case, r equals 1.1. All right, so if the next question was turn this into an explicit formula, all right, or explicit equation, what would we do? Well, we have two options. We could use f of 1, which is 110, so let's do that first. Okay, f of n equals f of 1, which is 110, times r, which we just found was 1.1, to the n minus 1. This would be the explicit formula for this sequence. Okay, but that's not how we did it on the previous one. On the previous one, we started with f is 0. So if we start with f is 0 is 100, and r is 1.1 to the n. Now, in a real life situation, like, right, when you started with 0 and then after 1 year it's 110, right, it makes sense to use f of 0. But when you're looking at just a sequence of numbers, right, it's going to make sense to start out at the first term because that's what's given to you. Right? But if the 0 term is given to you, then it makes sense to use f of 0. All right, let's look at it. One more example. All right, here we have a value of a car. It starts off brand new. You just bought the car. It's $20,000. 1 year later, it's worth $18,000. 2 years later, $16,200, and so on. All right, so we want to write the explicit equations for this sequence. So first thing we have to do is find the common ratio. All right, so this one is going down. It's decreasing. All right, so what am I multiplying by to make it smaller? So it's going to be a number in between 0 and 1. What is that number? So let's divide. 18,000 divided by 20,000. And that equals 0.9. Let's check one more, make sure it's the same every time. 16,200 divided by 18,000. And that is also 0.9. So in this case, my common ratio is 0.9. Right? It is decaying. All right, it's getting smaller, it's decreasing, okay, by a factor of 0.9, because that's what I'm multiplying by. But if I were to ask you, at what percent is it decreasing, okay, at what rate is it decreasing, interest rate, it would be 10%. Right? It's decreasing by 10% every year of the previous value, all right? So you got to make sure you know, am I asking for the rate or am I asking for the ratio? Okay, the ratio is 0.9. So do this up here, f of n. So the first term is 18,000 raised to the, or times 0.9 raised to the n minus 1. Or if I start at the original value of the car, it'd be 20,000 times the ratio, so times 0.9 raised to the n power. All right, so we should be able to look at a sequence of numbers and turn it into an explicit equation, all right, which is in turn is really an exponential equation because it's got a base raised to a power. All right, so your turn in the Edpuzzle video now to answer these two questions. Question 1, write the explicit formula for the geometric sequence. All right, now that you picked your answer, let's check it. So we know that we need to figure out r. So what am I multiplying by every time to get the next number? This one's a little bit more obvious than the other two examples we did. We're multiplying by 2. So r is 2. All right, if r is 2, then we could go ahead and use, this is the first term. So the explicit formula we're going to use here, since the first term is given to me, would be 3, the first term, times 2, raised to the n minus 1. All right, and if I wanted to use the zero term, it's not given to me, so it wouldn't make a lot of sense to use it here, but what number would come before 3? And that is 3/2. So it'd be 3/2 times 2 raised to the n. So same thing, just one's written with the zero term, one's written with the first term. All right, now you're going to do question 2. Write the explicit formula for this sequence. So this sequence is getting smaller, 64, 16, 4, 1. So each time I'm dividing by 4, but dividing is not with the common ratio, it's by multiplying. What am I multiplying by? So if I'm dividing by 4, I'm multiplying by 1/4. So in this case, r is 1/4. So my explicit formula would be 64 f of 1 times r, 1/4, raised to the n minus 1. Or if I wanted to use the zero term, which I don't know, so I got to figure out what would come before 64. So I multiply that by 4, and that's 256. It would be 256 times 1/4 raised to the n. All right, so that's our review on geometric sequences. Right, we need to know the common ratio. We need to know if we're starting with the first term or the zero term. We know which exponent to use. But these explicit formulas are turning into what we're now going to call exponential functions. And so we want to look at the parent function, okay, and look how these are graphed. All right, so the parent function is just simply y equals b to the x. There's no f of 0 in front. There's no f of 1 in front, right? There's no minus 1 in the exponent. This is really the f of 0 function, but f of 0 is always 1 in these parent functions. All right, so if you look here, we got two different graphs. So we got one parent function that can produce two different graphs. And why is that? That's because of our common ratio, which we're going to change that word now. All right, we're going to change that word to the growth or decay factor. All right, so what we called common ratios in geometric sequences, we are going to now call either growth or decay factor. Okay, if the b is between 0 and 1, so 1/3, 1/2, 2/3, any number between 0 and 1, it is a decay factor. All right, because that number is smaller than 1. So when you multiply it by a number smaller than 1, it gets smaller. All right, so decay is between 0 and 1. Any number bigger than 1 will be considered a growth factor, right? 2, right? It's doubling, it's growing. 3, it's tripling, right? So any number bigger than 1, it's growth. Any number between 0 and 1, it's decay. All right. Why can't it be 0 or 1? Well, if it's 0, 0 to any power is always 0. So that's not growing nor decaying. That would just be a horizontal line. That's a linear function, right? Same with b is 1. 1 to any power is 1. So that, again, that would just be a horizontal line. So it's not growth or decay. And then why can't b be negative? So let's take a real quick look at that. All right. So if I said that y equal -2 to the x, right, and I start to make a table of values for this, and I plug in -1, actually, I'm not even worried about that. If I just plug in 1, -2 to the first is -2. If I plug in 2, -2 squared is +4. If I plug in 3, it's -8. If I plug in 4, it's +16. So this function, right, is negative, and then it's positive, and then it's negative, and then it's positive. This function would be growing, then decaying, and then growing, and then decaying. We call that an oscillating function. So that is not considered an exponential function. All right, so B has its restrictions, okay? B has to be either between 0 and 1, and that makes it a decay factor, or greater than 1, and that is a growth factor. You should be able to look at a graph and tell if it's growth or decay, right? And we're talking about end behaviors really control that, right? If the end behavior is going towards positive infinity, right? The right end behavior, is going then to positive infinity, then it's growth. If the right end behavior is going towards an asymptote, towards a constant number, then it's decay. All right, so let's look at a couple examples on graphing. So let's graph f of x equals 2 to the x. So here my growth factor is 2. All right, so we're going to start by making a table of values. I plug in -2, what is f of -2? All right, so we just went over our properties of exponents last unit. So we know that anything raised to a negative power just means you're taking the reciprocal of it. So it's 1 over 2 squared, which is 1/4. All right, and then we do the same thing for -1, f of -1. Plug that in, 2 to the negative first is 1/2. All right, anything raised to the 0 power is 1. 2 to the first is 2. 2 squared is 4. Right? If you look, these are just all being multiplied by 2. This is a geometric sequence over here, just doubling every time. All right, so what is this graph going to look like? So let's plot these points. All right, so -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4. So you can see how it's curving up, right? If I plugged in 3, I would have got 8. But notice how it's never getting to be 0 over here. When I graph this, this line can never go below 0, and we'll talk about that here in a sec when I'm done drawing it. Okay, so there's my curve. And so why can't it be 0? What if I plugged in -100? It's going down the whole time. So why would it not go down? Because it's 2 to the -100th, which just means 1 over 2 to the 100th. So that's still positive, right? Nothing's going to make that negative. This graph will never go below 0, never equal 0. It's going to get really close, but it'll never equal it. Okay, and so what do we call, right, this? We learned about this when we did rational functions. The graph gets really close to it, approaches it, right? It is called an asymptote. This is a horizontal asymptote, all right, which is going to affect our end behaviors, right? So what is the left end behavior in this problem? If I said, as x approaches -infinity, which means the left end behavior, what is y doing? Here, y is approaching 0. It's approaching that asymptote. All right, and then what's my right end behavior? As x approaches +infinity, now that one's going up forever, so y approaches +infinity. Okay, so our end behaviors, okay, are controlled by our asymptotes. Right? If it approaches the asymptote, that's our end behavior. If it's going away from the asymptote, then it's going towards infinity. All right, so our domain here, right, it's going to go left forever, it's going to go right forever. My domain is just simply all real numbers, and that'll be true for any exponential function that has no real life constraints on it. The range, though, is not all real numbers. It is restricted by that asymptote. It's never going to go below that asymptote. So the asymptote's at 0, so it's never going to go below 0. It's actually never going to equal 0. So it's 0 to infinity, both in parentheses. No bracket here because it doesn't equal 0. All right, so this is our growth factor. We have horizontal asymptotes, we have our table of values, we got to identify our domain and range, and our end behaviors. All right, now we're looking at a decay function. How do I know it's a decay function? Because my b is in between 0 and 1. All right, so it's 1/2. So this is a decay function. Let's start with our table of values. So now when I plug in -2, I'm going to get 1/2 to the -2nd. And so a reciprocal of that would be make it 2 squared, which is just 4. And then let's just use the pattern. We know it's going to be multiplied by 1/2 every time. So 2, 1, 1/2, 1/4. So very similar numbers, they're just in different order. So this one, instead of going up, it's coming down towards the asymptote. So at -2, 4, -1, 2, 0, 1, 1/2, and 2 1/4. So this is a decay function. Okay, it's going down, it's decaying. Again, it never goes below 0. Oops. All right, and then we could draw our asymptote to kind of show that it never went below 0, even if I accidentally did. All right, so looking at our end behaviors now my left end behavior is going up. So my left end behavior as x approaches -infinity, y is approaching +infinity. And my right end behavior now is the one that's approaching the asymptote, which again is at 0. So as x approaches +infinity, y approaches 0. Okay, my domain, all real numbers. And my range, again, it never goes below 0, so 0 is the smallest number. Infinity is the biggest, and it never touches 0, so parentheses. All right, so these are our graphs. Okay, this is a decay function. It's going down. During block 1, we'll talk about A, H, and K, so we could shift this graph up. We could reflect it. We could shift it to the left and right. We can do any of those same things with our A, H, and K. We'll talk about that more during block 1. All right, here's your opportunity in the Edpuzzle now to answer these questions about the function y. Your f of x equals 3 to the x. We got the equation here. We got the graph here. Go ahead and answer these 5 questions in the video now. Okay, is the function growth or decay? Well, you could tell 2 ways. B is bigger than 1, so it's growth. And you can just look at the graph. It's increasing, right? So that's growth. So this is a growth function. All right, so what is the growth decay? Or sorry, the growth or decay factor? This is a growth factor. We already answered that question. So the growth factor is what? It's our B. So whatever B is. So this is 3. All right, now we want to evaluate, so we want to plug in -1, or you can look at the graph if you could determine from the graph. If you can't, we want to plug it in. F of -1 is going to be 3 to the negative first power, which is 1 over 3. So F of -1 is 1/3. F of 2, okay, can we look at the graph and tell? Okay, it does look like we can. That looks like it's at 9. Let's double check. F of 2 is 3 squared, which is 9. All right, the domain, right, is all real numbers. And the range is everything greater than 0, so 0 to infinity in parentheses. All right, so that's our introduction to graphing exponential functions. Right, again, like I said earlier, we're going to explore A, H, and K later. And then we're going to actually tie these into real life situations, and you guys could learn about the power of compounding interest.